In this video, I want to say a little bit about using fast Fourier transforms in Matlab. So I'm not going to introduce you to fast Fourier transforms. If you don't know how those work, go to the library and get some books or something. I'm just going to show you how to implement them in Matlab, and I'm going to use some stuff I downloaded from the web to simplify things a little bit. I'll walk you through all that as we go. So it's pretty straightforward to take an FFT of any data set in Matlab. I'm going to assume in this that the data has been collected at a constant sampling rate, right? So there's an equal time between data points, and it's trivial to do. The only tricky thing is connecting what you get to a frequency, and I'll show you how to do that as we go. So here's just an example. Most of this script is just generating a set of data. So the first 7 lines of this are just generating the data set using a sine wave, and then the real interesting part is just this FFT command down here. So I'm creating a sine wave with a frequency of 4 hertz, and I'm sampling it at 100 times a second. So the sampling period is 1 over 100, or a hundredth of a second. And so I set up a set of times going from 0 to 1 minus that sampling time, incrementing by the sampling time. I set up a number of samples, and then I just calculate the sine function. I picked an amplitude of 2 for no particular reason, but I use f naught as a frequency. So we get this 4 hertz sine wave. And then I just plot the sine wave. But then I use the built-in FFT command in Matlab, and I get the FFT. I get it. The results are complex. Okay, so this Y freak domain variable contains the complex results for that FFT, and then to plot it, I take the absolute value of those complex numbers and then do a stem plot. And the FFT should pick out these frequencies, so we should get a spike at plus or minus 4 hertz. So here's what it looks like. It may be difficult to see, but you get one spike here and one spike here because of the nature of the FFT. You get this plus or minus 4 hertz. But notice the x-axis here goes from 0 to 100 because I used roughly 100 samples. So it's just plotting versus the sample number. And we don't really want that. We want frequency down here so we can line up these at plus or minus 4 hertz. Now there's a variety of ways to do that. I've chosen to download a routine that does it automatically, okay? But basically, it comes out of the sample rate or the period between samples, and from that you can calculate the frequency. I prefer to use a routine that does this automatically. So I got this from blinkdagger.com. It's an interesting blog related to these sorts of things, okay? And on that website, I downloaded this routine called positive FFT. It gets rid of this plus or minus symmetry in the FFT, so it dumps out half of the results, and then it returns not only the FFT but the frequency. All right, so I'm not going to go through how this works. All I know is I send it a set of data, time samples, and a period between samples, or a sample rate actually, and then I get back a set of FFT values and for each of those a corresponding frequency. Then we can plot the absolute value of x versus this frequency and get it the way we want it. All right, so check out blinkdagger.com if you want this script. So now we have the same, in this case, 6 commands that generate our values, and then we just call the positive FFT routine using the sample data and the sample rate fs. And it returns y freak d is the FFT, freak range is the frequency. So then we do a stem plot using freak range as the x-axis and then the magnitude of the y freak d as the y-axis. So now we get this. Again, we split off the symmetric part of this, so we're only looking at positive frequencies. The frequency now goes from 0 to 20 hertz, and you can see this big spike at 4 hertz, which is just what you'd expect from a single frequency sine wave. All right, so using that command, it's trivial to do FFTs. So now let me take a look at a quick example. Okay, we're going to import some data and use the FFT on that data. I downloaded a file, touchtone.mat, from Cleve Moeller's website. He has a nice textbook called Numerical Computing with Matlab, and the associated website has this file in it. So you can download this touchtone.mat. It contains an 11-digit phone number sampled, right? So it's the sound file for an 11-digit phone number. So what I do is I load that file, touchtone.mat. I say load touchtone, and the sample rate is contained there in y.fs. And down here, I take the first 8,000 samples out of there to reduce the 11 touchtone touches to just one. So I take one touchpad press and I sample it. So now Y contains the time sample data, and I can plot that, and it looks like this. Okay, so this is the sound wave for a single touchtone press on a touchtone phone. Now I want to take the FFT of that. Okay, so I use my positive FFT routine on Y using the sample rate, and I do my stem plot, and you can see there's two numbers which predominate. One is right around 700, and the other one is right around 1200. And it turns out you can figure out which number was touched by connecting these frequencies up um, to the scheme used for touchtone phones. So you can see how each of these frequencies, 697, 770, 852, give you a row in the touchtone touchpad, and these ones 1209, 1336, and 1477 give you a column. So you take the two numbers from this from the FFT of a sample, and again we got 700 and 1200. So the 700 tells us we're in row 1, and the 1200 says we're in column 1, and that means that number touched was a 1. So it's the beginning of a long distance number. You always start with 1, at least in the US anyway. So anyway, that's how you use these FFTs. If you download this positive FFT routine from BlinkDagger, then you should be in good shape for applying FFTs to whatever sample data you want. You might look on the Matlab help. There's a good example of looking at sunspot data using FFTs. Thanks.